Hi class, this video is going to help with section 11.2 in Business Calc or 4.2 depending on the version of the book. Okay, so what we're doing in this section is very similar to 11.1. We're going to find the second derivative and see what that tells us about the original graph. So in the section before, we found the first derivative, or the regular derivative, right? And we said where it equals 0 is our critical value, or where it's undefined, and then we use those to find where it's increasing and decreasing. Well, same idea. What if we found that second derivative and we set it equal to 0, and what would that tell us? So that's going to tell us about concavity, or where something is concave up and concave down. So let's look at concave upward first. So we would say I am concave up on an interval from A to B, so A to B, or 0 to 1, or whatever the interval is. If the derivative is increasing from A to B, so the derivative is increasing, and the second derivative will be positive for us to be concave up. You'll note that the tangent line is below, okay? So it'll look like this. Concave up is just got a curve upward. It could be a full U upward, like I'm showing with my hands. Or it could look like part of it concave up. So if I'm concave down, it's going to look like this. Okay, and my tangent lines would be above if I'm drawing my tangent lines. And for this one, your derivative would be decreasing. Okay? So this is what concave down looks like. So don't be too worried about increasing, decreasing. We already know how to do that. We can separate them. But if I'm concave up, I'm curved upward. If I'm concave down, I'm curved downward. That's the big idea there. Okay, so this brings in the idea of a second derivative. So that's something we haven't seen before. So the second derivative is the derivative of the derivative. That's it. So we have lots of notations for that. This is our most common, the double prime. Okay, or you could see derivative d dx of the derivative, so derivative of derivative. Or you could see d squared y over dx squared, saying a double d dx. That's a weird one. That means second derivative. And the y could have the prime on it too. So f of x is function notation, or it could have the y. So let's look at an example of just finding that second derivative before we start to look at if something's concave up or down. So if I have something like my original function is equal to x to the third, okay? What would be the derivative of x to the third? Well, the derivative is going to be 3x squared. Now then take the derivative of the derivative, and I would then get 6x to the 1, or 6x. All right, there we go. So we can do that derivative of the derivative. Now I am going to do one more of just finding the second derivative. Let's try one that's a little bit harder. Well, what would be e to the x? I do have that. So what's the derivative of e to the x? Well, it's e to the x. Here. What if I just want to do the second derivative of this one, just for practice? So what if my f of x is equal to the natural log of x squared minus 4x plus u? So what's the first derivative of this ugly thing? Well, this x squared minus 4x plus 5 is inside of a natural log. So we have to use the chain rule. So we're going to say, all right, the original derivative is going to be, we would do 1 over x, but instead of x, we're going to do 1 over all of our original inside part. And then what do we have to times it by once we do the derivative of the outside? We have to times it by the derivative of the inside. So the inside derivative would be 2x minus 4. So when we're done, we could think of this as over 1. Our final answer will be
2x minus 4 on top over x squared minus 4x plus 5.
Okay, not real pretty. Brings up that chain rule and all those rules of our derivatives. Okay, I'm not even done. Now I want to do the second derivative.
Okay, so if I go to the second derivative,
What is that going to bring up for you?
it is going to bring up, there's the rest of my answer right here. It's going to bring up
Our quotient rule. Okay, so what does our quotient rule say? It says take the low d high, high d low. So we're going to take
low, that's this one. So x squared minus 4x plus 5 times the derivative of the high, which is minus the top, the high, times the derivative of the bottom. So the derivative of this one would be 2x minus 4.
So low d high, derivative of the top, minus high d low, all over low squared.
We don't need to simplify.
I did this one because the derivative's kind of ugly. Second derivative is even uglier. So it brings up our chain rule, and it brings up then our quotient rule. Okay, so those are our second derivatives. Now, what am I going to do to decide if something's concave up or down? We have to decide first where it's positive and where it's negative. So where is it greater than 0 and less than 0 on our second derivative? So let's start with looking at this function that we just did the derivative of, x to the third, like a basic one. And let's find where it's concave up, concave down, and we're going to find something called the inflection point. Now, an inflection point is just where you can change from concave up to concave down.
So let's start with, we know that second derivative is 6x. So for an inflection point, we set that equal to 0.
And we find where does the second derivative equal 0. That should look familiar because we did our first derivative where it equaled 0, and that gave us where it could switch from increasing to decreasing. So same idea here, but it's going to switch from concave up to concave down. So this is okay. The x value is, if it happens to ask for the full point,
what we would do is we put the 0 into our original function.
And I want to write that kind of weird like that, just to remind you of I'm putting that 0 into. So if I put 0 into the original function, I get back out 0 because the original function was x to the third. 0 to the third is still 0. So our inflection point for this one is 0, 0. Now, how am I going to decide if it's concave?
Well, that's where the second derivative is greater than, not or equal to
0. I'm just writing random slashes here now. So twice. So where is this greater than 0? Well, if I divide the 6 on both sides, I still get 0.
So where x is greater than 0,
it is concave up.
So that would also could be 0 to infinity.
If you wanted to write it in that notation as well.
So concave down is where is my second derivative.
So where is that second derivative
less than 0? So for this one, it is just
less than 0 because 0, 6 divided into 0 is still 0. So that is going to say negative infinity to 0 is where you're concave down. So these are the three things I can tell using a second derivative. Inflection point, where it changes from concave up to concave down. Where is it concave up? Where is it concave down? Now I'm going to go to Desmos real fast and type in our original function, which is x to the third, and I'm going to look at the original. Look, here's 0, and below that, your concave down, which is what we just said. And above that, your concave up. So I found this third derivative, or excuse me, second derivative, where it equals 0. That's this inflection point. And I found where it's concave, concave up and down of the original. So again, I'm using the second derivative to tell me something about the original function. So your exam on this will have a problem where you cannot use Desmos, and you have to use these ideas to tell me stuff about the original function. Okay, so let's do another example that's harder. Yeah, so that one's kind of ugly. That one's. What if we did, let's do the one we just did. Okay, so this is my fourth problem, and our original function was the natural log of x squared minus 4x plus 5. And we already found the second derivative to be ugly, x squared minus 4x plus 5 times 2 minus 2x minus 4 times 2x minus 4 all over x squared minus 4x plus 5 squared cubed. Where are my inflection points? That is where this equals 0. Okay, I'm feeling lazy about writing this down again, but I need to. So where does it equal 0? So x squared minus 4x plus times 2 minus 2x minus 4, 2x minus 4, all over x squared minus 4x plus 5 squared. Where does that equal 0? Okay, what I love is the denominator times 0 is 0. Shoop, denominator's gone. Thank goodness. So this is gone because this times 0 is 0. So now I want to simplify that top. So I'm going to multiply the 2 throughout, and I get 2x squared minus 8x plus 10 minus this entire thing. So I'm going to add a parenthesis, and I'm going to simplify here. 2x times 2x is 4x squared. 2x times 4 is a negative 8x. Negative 4 times 2 is a negative 8x. Negative 4 times negative 4 is a positive 16. Okay, where does that equal 0? So these are all going to be opposite signs because it's a minus it all off. That's where most people are going to make a mistake if they do. So I'm going to change this to positive, that's to a negative, that's to positive, negative. Then I don't have any mistakes that I can make. So I just subtract them all off. So these two are the same terms. So that's negative 2x squared. That one and that one, we already did these, are going to cancel each other. And then I'm going to have a positive 8x and negative 16 and 10 is negative 6. Okay, where does that equal 0? You could use the quadratic formula or you could factor. Okay, so I'm going to take a negative 2 out of everything because I can't do my factor rules with a negative 2 out front. So this is going to give me x squared minus 4x plus 3 equals 0. So this does not have an x with it, so it's not going to really play a role in our answer. So we're going to factor this part, and we're going to get x minus 3, x minus 1. Negative 3 times negative 1 is going to equal positive 3, but they add to the negative 4. So that gives me x equals 3 and 1. Holy moly, that brings up a lot of algebra, so you need to go carefully, and it might take you a couple tries on some of these problems. Okay, so we're here. Now we know if we did a sign chart, we have a 1 and we have a 3. Those are our inflection points. Now I didn't find the y values. If you have to, you're going to put those values into the original function, and that will give you your y values on those two inflections.
Okay, these are zeros of our second derivative.
And we need to decide if we're negative or positive in each section.
So we're going to say, all right, 0 is below 1. So if I put a 0 in to the second derivative,
ooh, use your calculator, okay? 0 in here is actually going to give me a negative. Okay, I don't really care what the number is. A 2 in here is going to give me a positive. And a 4 in here will give me a negative. So putting in a number like I use 2 here and I use 4 here, you're just going to be calculating that out. It's kind of a pain. So make sure you calculate the numerator, calculate the denominator, and then divide them and see if it's positive or negative. So what does the negative tell me? Concave down. What does the positive tell me? Concave up, and another negative of concave down.
So we are concave down from negative infinity to 1, and again from 3 to infinity. We are concave up from 1 to 3.
All right, up just a little. Whoo! So we can still use the sign chart, or if it's like an easier function, you can see where is it greater than 0, where is it less than 0. That is going to bring up whether you remember how to set up to get your two solutions on an x squared with less than and greater than. Totally, you can do it that way. I like that way for a basic one like x to the third, x to the fourth. Even if it has a 2x and a 3 and whatever numbers, still that's a great way to do that one most of the time. But the sign chart, all you're doing is putting in values and finding if it's positive or negative. So this method is my favorite method. This is also the way your examples will do it as well.
Okay, so what I do is no, I thought I had one that was a little harder. I think that one was probably my hardest one.
E to the x is just funny. All right, so you have plenty of other examples in the book. So this will give you an idea of that second derivative, how to find it, and also how to use it to tell me if we're concave up or concave down. And yeah, if you want to go into your Desmos and graph this thing and see if you're correct. So you graph the original to see what that, where it's concave up and concave down. Anyway, there's lots of other videos that you can use if you need to as well.